Hi, my name's Tony Preston, and in this short video we're going to run through some of the basic functionality of Agilent's N9344C 20 GHz handheld spectrum analyzer. If you want to learn more about the N9344C, make sure you get a copy of the complete user training and application tutorial DVD, which you can obtain free of charge from Agilent. It runs for about an hour and provides far more detailed training on a whole range of practical topics, such as making interference measurements, measuring the modulation characteristics of carriers, sweeping diplexers, and other practical measurement examples. And if you've not done so already, you might want to download the PDF of this Agilent N9344C demonstration guide so you can follow along during the course of this presentation. Let's start with a quick overview of the instrument. As you can see, the instrument is extremely rugged and ideal for field operations. In addition, it has a bright, daylight viewable transflective display, ideal for use outdoors in bright conditions. But when working in a communications room or other dark environment, the built-in light sensor can be set to automatically reduce the screen's brightness, making the display easier to view and saving battery life. And when we dim the studio lights, you can see that all the front panel keys have a backlight that can be set to automatically turn on when required. Just refer to page 6 of the demonstration guide for details on how to configure this. Here's the main power button. Just press that to toggle the instrument on and off. And to the right are a range of function keys. Pressing these selects functions such as frequency, span, amplitude, and bandwidth, etc. And if we press the Shift button, we get an additional range of functions such as save, display settings, sweep controls, and limit lines. There are the normal 3 methods for data entry using either the numeric keypad, the up-down arrow keys, or by turning the knob. And to the right of the display are 7 soft keys, the meaning of which changes depending on which function key we press. And probably the most important button on the instrument is the green preset button. Pressing this once presets the instrument to a factory default state, clearing any strange settings that a previous user may have set up within the instrument. But pressing and holding this button for more than 1 second performs another incredibly useful feature, and that is to put the instrument to sleep. Unlike turning the instrument off, putting it to sleep retains all of your current instrument settings. Just press the green preset button briefly once again to bring the instrument back to the same state you had it before putting it to sleep. On the top panel we have the main RF input, the DC jack for externally powering the instrument or charging the internal battery, a small USB connector for connecting the instrument to a PC, a large USB socket for a USB memory stick, audio headphone out for listening to demodulated audio, an Ethernet connector to connect the instrument to a local area network, an RF output socket if you have the internal tracking generator option installed, a probe power socket for connecting an active RF probe, a dual purpose BNC socket for connecting an external 10 MHz reference clock or externally triggering the spectrum analyzer. And even though the instrument has a built-in GPS receiver and internal antenna, you can also connect an external GPS antenna to this socket here. Let's start by making some simple measurements of a 2 GHz RF carrier, which is being generated by this Agilent MXG signal generator I have here. If you're following along in the demonstration guide, please turn to page 7. Now I've set the signal generator frequency to 2 GHz and the output level to -10 dBm and turned the RF on and connected the signal to the N9344C analyzer. So we'll start by pressing the green preset button and then enter a frequency of 2 GHz. And then let's press the span button and zoom in to, say, a span of 10 MHz. So that zooms in on the signal. And then we can move that signal to the top graticle by pressing the amplitude button and setting the reference level to -10 dBm. And there you can see the signal on the screen. And if we want to measure the amplitude of that signal, I can simply press the marker button. And here you can see the marker M1 is at 2 GHz and about -11 dBm. And while we've got that signal on the screen, let me just turn on some modulation. So that's a spread spectrum WCDMA signal, and let's see how we might make a measurement of that as well. If I press the mesh button and press channel power and set the integration bandwidth to say 4 MHz and a span of 10 MHz again like we had before, you'll see now very quickly and easily I'm measuring the total power under that modulated carrier. The channel power in the 4 MHz bandwidth is about -11 dBm, and the power spectral density in dBm per hertz is approximately -77. One key specification of any spectrum analyzer is its sensitivity. In other words, its ability to view and measure very small signals. So let's take a quick look at how well the N9344C performs in that regard. We'll start by pressing the green preset button to clear the previous settings. I'll disconnect the signal generator and replace that with a 50 ohm termination to ensure that no signals can leak in from outside through the RF input port. And then let's select a typical microwave frequency, let's say 18 GHz. So I'll press center frequency, 18 GHz, and we'll zoom in a bit. So I'll press span, and let's enter a span of say 1 kHz. You'll see the traces disappeared off the bottom of the display, so I'll press the amplitude button, and using the arrow keys I'll bring the trace back up onto the screen. I'll then press the attenuation button to remove all attenuation. I'll set that to 0 dB. That gives us an extra 10 or so dB of sensitivity. And I'll also turn on the internal preamplifier. I'll now press the trace button and more, and I'll turn on averaging. And now if I press the marker button, and you'll see at 18 GHz, we're measuring an incredible sensitivity of around -145 dBm. When out in the field, we don't want to have to set up each measurement from scratch every time. So let's see how we can use the N9344C's save and recall capability to save and recall instrument states. And also how to save a screen capture of the measurement results for including in a report, for example. Here I'm going to be saving files to the analyzer's internal memory, but be aware you can just as easily save and copy files to and from a standard USB memory stick that you insert into the top of the instrument. Let's start by saving the current instrument state into the internal memory so we can quickly recall it the next time we're out on site. So I'll press Shift and File, and if we press Save As, we can select Trace, or in this instance Instrument State, an STA file. I'll change the name, I'll call it A001, and press Enter. You'll see here that the file A001, which is a state file, has been saved to the internal memory. You'll see here the media type is internal, and it was saved at 1:45 in the afternoon on the 30th of April. Now, if we get out of that screen and I press the instrument preset button, we go back to the factory default state. I can now quickly recall that measurement we had of channel power of the CDMA signal simply by pressing Shift, File. We'll scroll down to A001 and I press the recall button, and you'll see the instrument has immediately recalled all of the instrument settings that we'd previously been using. Everything from frequency span, amplitude, attenuation values, even the automatic measurement that we had for channel power. Not only does this save a lot of time when you're out on site, but it also increases the quality of the measurements that you and your team are making, because it means that the same measurement can be made the same way every time, regardless of the operator and regardless of which instrument you're using. So we're out on site and we've made the measurement that we want, and now we need to save the screen capture of the results for including in a report or emailing to a client. Now there's a very quick and easy way of doing this, but I'll just show you how to set it up first. If I press the Shift and File button again and press the Setup button, You can see here there's a setup for what's called the quick save. The quick save type of file is currently set to JPEG, and quick save auto naming is off. I'll turn it to on and then press return, and we'll go back to the main screen. Now, to save that screen image as a JPEG file in internal memory and for copying later onto our USB memory stick, all I have to press is Shift and Save, and the instrument prompts us automatically with a name, and here you can see the file name ends with _5. I'll just press Enter. The instrument's now saving that JPEG file to the internal memory. And if we then decide to make another measurement, and I want to save the results of that, I'll just press Shift and Save, and it prompts us with a new name. The same prefix as before, but now _6, so that's the auto naming feature in operation. I'll press Enter again, and both of those images have now been saved to the internal memory of the N9344C. And for those of us involved with defense and security operations, be aware that if you order option SEC, Secure Erase, you have the ability to perform a low-level format of the entire user memory and delete all user data. This is made possible by the careful design of the N9340 series of analyzers, where user data is stored completely separately from the internal system memory. So with option SEC activated, all user data can be permanently deleted and cannot be recovered. Ideal if you need to send the unit off-site for any reason. In the previous section, you saw how we turned on a normal marker to measure the amplitude of a signal. But Agilent's handheld spectrum analyzers have many more useful and sophisticated marker functions that are worth knowing about. If you're following along in the demonstration guide, refer to pages 17 and 18 so you can follow along. You'll see I've disconnected the signal generator and replaced it with this cheap whip antenna, and we're going to tune into the FM broadcast band. So having pressed the green preset button, let's enter a start frequency of 88 MHz and a stop frequency of 108 MHz. Then to improve the sensitivity, I'll press the amplitude button. We'll set the attenuation to 0 dB. I'll turn the internal preamplifier on. And so that we can identify those individual FM broadcast transmitters a little more clearly, I'll press the bandwidth button, and using the down arrow key, we'll reduce the resolution bandwidth down to 100 kHz, and we can identify each of those carriers a little more clearly. If I press the shift button and then peak and peak search, you'll see that marker 1 goes to the top of the largest signal on the display. But now here's a useful function. If I press more and peak table and turn the peak table on, you'll see that 10 markers have been turned on, and they have gone to the peak of the largest 10 signals on the trace. And at the bottom of the display you can see a table here showing that marker 1 is at 97.7 MHz and the amplitude level is -51 dBm, and you can see those frequency and amplitude values for all of the 10 markers, and they're all being updated in real time. But let me turn the peak table off, and I'll press the marker button again. And if I press the mode button here, you'll see, well, currently marker 1 is a normal marker, but if I press the mode button, you'll see we've got a range of other functions. We can press the delta button so that we can measure the difference between this carrier and this carrier. I'll just show you that. If I press delta, marker 1 now reads 0 Hz and 0 dB. And if we move that delta marker to the next largest signal to the right, you'll see that that second signal there is 1.56 MHz higher than the main signal, and it's about 3 dB lower in amplitude. I'll go back to normal marker for a moment and return. And if I press the function key, you'll see that we can turn on some other useful features too. If I press the noise marker button and move the marker across to the noise floor, You'll know from Boltzmann's law that to measure the noise floor amplitude, we can set that to any value we want simply by adjusting the resolution bandwidth. So the noise floor is normally measured normalized to a 1 Hz bandwidth, and that's exactly what this noise marker does. You'll see here that the marker here is showing that the noise floor is minus 141 or minus 142 dBm per Hertz. In other words, normalized to a 1 Hz resolution bandwidth. And you'll see there's a band power function that allows us to measure the total power within the integration bandwidth of a modulated carrier. But below that, there's a demod capability. Let me just move the marker back onto the top of one of these FM carriers. That one will do. And I'll press the demod button. Now you'll see the demod setting is currently set to AM, and of course we're in the FM broadcast band, so I'll press demod setting and select the demod type to FM. And I'll turn the speaker volume up to the maximum, which is 100. And currently what's happening is the analyzer is pausing at the end of each sweep for 100 milliseconds and demodulating that audio. So if I change the delay time to 10 seconds, we can hear the demodulated audio from that radio station and listen through the internal speaker. I'll turn that down. Or through the headphone socket, of course, on the top panel. Measurements of interference, security surveillance, and site surveys of RF transmitters all involve the measurement of intermittent or time-varying signals. And this is where the spectrogram capability of Agilent's handheld spectrum analyzers is invaluable. If you want to see a more detailed example of how the spectrogram feature works, please request a copy of the application and tutorial DVD I mentioned earlier. But for this demonstration, we're going to look at a common situation up in the microwave bands where, having connected a suitable antenna to the analyzer, we end up seeing little or no RF activity for a long while, but have a critical requirement to capture any signal that might suddenly appear and then disappear just as quickly. Having an operator sit here watching the RF spectrum trace just in case a signal appears is a ludicrous waste of manpower and resources, when the spectrogram feature can perform the task automatically for us. So I've set the center frequency to 18 GHz, the span to 2 MHz, and I've set the resolution bandwidth down to 3 kHz. And amazingly, we still have a sweep time of 84 milliseconds. I've set the attenuation to 0 dB and turned the preamplifier on to maximize our sensitivity. And you'll see the noise floor is roughly around minus 120 dBm. And here's a typical display you'll see of the microwave bands. No activity whatsoever. But then, every now and then, there's a carrier that pops up. There it is again. Now it's going to be almost impossible for me to try and attempt to make any measurements of that signal with it being so intermittent. So let's turn on the spectrogram measurement and see what it can do for us. I'll press the Measure button and then Spectrum Monitor. And you can see now the display has been divided into two sections. At the bottom half we've still got the yellow trace, showing the spectrum analyzer trace in real time as we saw before. But on the top section here we now have the spectrogram. The x-axis is still displaying frequency, but the y-axis is now showing time. What we've got here is a history of all the different spectrum traces stacked on top of each other. And the amplitude of the signal is now displayed by the colour of the trace. Red or yellow indicate a strong signal, and blue or green indicate a weak signal. And you can just about see here the dashed intermittent signals that we were monitoring before. But let's try and make that a little bit clearer. If I press the amplitude button, let's change the scale per division to 5 dB per division. And let's change the reference level to minus 60 dBm. Now that looks quite good, doesn't it? So the background noise here is just showing a solid blue colour, and we can see the amplitude of these intermittent signals here coming up in white. We might just adjust that one step further. Now you can see the noise floor more clearly, and we might catch any even weaker signals. So if I press the Measure button again, we can pause or run that spectrogram measurement. We can restart the measurement. That clears all the previous saved spectrum traces that we had stored. And if I press the update interval here, you'll see it's currently set to 100 milliseconds, which is the fastest rate you can go. But I can change that to, say, every 10 seconds or every minute if we want the instrument to pause for that period of time before sweeping the new trace. We can view it in grey or in colour. And we can press the display mode button and convert the whole screen to the spectrogram trace if we want. But my preference is to have both showing at the same time. Now here's the really key feature of the spectrogram logging capability on Agilent's handheld spectrum analyzers, and that's file logging. So I'll press the file logging button and I'll press Start Save. Every trace, every spectrum trace in the spectrogram is now being stored into the internal memory, time and date stamped, and it's even logging the GPS location from the built-in GPS receiver that I've turned on. And here's another great feature. With the time setting, I can tell the analyzer not to make the measurements now, but to start on a particular date at a particular start time, and then log until the stop date and stop time. So if you want to make interference measurements late at night or over the weekend, you don't need to have someone sat there all weekend monitoring the spectrum. We simply set the time save condition to the time and date that we want. I'll press return, and I'll press stop save. Now, all of those spectrum traces have been saved to the internal memory, so let's recall them. I'll press Shift, then File, and we'll view file type of trace. And you'll see here, if I scroll down with the knob, here is the trace that we've just saved at 21 minutes past 3 on the 30th of April. So I'll recall that. And here now you can see the recalled trace data that we've just stored. Now, if I press the marker button, marker 1 is there and turned on. I'll press marker 2 and I'll turn that on as well. You'll see here marker 2, a white cross in the center of the display. I can now press the frequency button and move that cursor across the screen. And let's line it up with that intermittent signal. You can see here now marker 2 is not only shown by the white cross on the spectrogram trace, but also by a normal number 2 marker on the turquoise coloured trace on the lower half of the display. And you can see marker 2, that interfering signal is at 18.000647826 gigahertz. Its level at that point was minus 99 dBm. And if you look at the bottom of the display here, you'll see marker 2, there's a time value. So that particular trace was at 21 minutes past 3 and 0 seconds. If I now press the time button, I can now scroll back through time. You'll see the white cross there for marker 2 on the spectrogram trace moving up the spectrogram display. And you can see that the previous burst occurred at 15, 20 and 53 seconds. This is an incredible capability having this built into a handheld analyzer. There's no external PC or storage device required. We're logging both the frequency spectrum, accurate measurements of frequency and amplitude, and the time value at which they occurred, plus the GPS location that we were at the time the measurement was made. Now, here's a feature you wouldn't normally expect to see in a handheld spectrum analyzer, and that's the ability to have different detector types active concurrently, each one on a different trace and all sweeping simultaneously. There are a number of applications where this capability can be a real time saver. For example, when measuring the broadband amplifier output from a satellite transponder, or even the power amplifier output from a 3G mobile phone base station transmitter, where you might want to measure the crest factor of the noise-like output from these devices. Here, we're going to look at the output from a spread spectrum transmitter at 2 GHz. So following along in the demonstration guide on page 20, I'll press the green preset button, and then enter a center frequency of 2 GHz, a span of 10 MHz, and a resolution bandwidth of 10 kHz. It then tells us to set the reference level to minus 30 dBm, and to set the scale per division to 2 dB per division. Now currently we're viewing trace 1, that's the yellow trace on the analyzer, so if I press trace button, more, we can select the detector here and make sure it's set to positive peak, which it is. I'll press return and turn averaging on. We'll then press the More button again and select Trace 2, set that to clear right. If I press the More button, we can set the detector for Trace 2 to negative peak. And again, let's turn averaging on. And if I press the bandwidth button, we can set the average type to power averaging. Now let's press the trace button again and turn on trace 3. We'll set that to clear right. And if I press more, we can set the detector type to averaging RMS and turn averaging on. So incredibly, each time the analyzer sweeps, it's simultaneously making measurements of both the positive peak, the negative peak, and the RMS average value of the incoming spread spectrum signal. For further information on the N9344C, just go to the website shown below. Here you can download datasheets, manuals, a copy of the demonstration guide, and even request a free copy of the user training and applications tutorial DVD I mentioned earlier.